Previously, we were able to fit a line on the scatter plot based on the least squares approach. But how do we know how well the model is explaining the underlying data? We're going to use two measures. The first measure is called R-squares, and the second measure is called SER, or standard error of the regression. How do we think of the fit for a regression model? Visually, if the observations are very spread out around the regression line, it's most likely we haven't explained the data very well. But if the observations are very tightly wrapped around the regression line, then it's possible that we have done a good job fitting the model to the underlying data. How do we formalize a measure to quantify the goodness of fit in the model? Before we introduce the fit measures, we need to define a few things. The first one is SSR, or sum of squared residuals. Recall that residual is defined as the difference between the actual y and predicted y. If you square the residuals and then sum up all the square terms, then you have SSR. SSR explains the amount of variation in y that is left in the residuals, or the amount of in the residuals, or the amount of variables in y that is not captured by the model. The second measure is TSS, or the total sum of squared. TSS is defined as the sum of squared differences between y's and y bars. TSS explained the total amount of variation in the y variables. The third measure is ESS. ESS, or the explained sum of squares, is defined as the sum of squared differences between predicted y's and y bars. ESS explains the amount of variation in the y variable that is already explained by the model. It can be shown that TSS, total sum of squares, is equal to ESS, the explained sum of squares, plus SSR, or sum of squared residuals. R-square is the most frequently used goodness of fit measure for linear models. Mathematically, R-square is defined as ESS divided by TSS, or 1 minus SSR divided by TSS. In the one variable regression case, R-square measures the fraction of the sample variation of y's that is explained by x, or the only independent variable in the model. R-square ranges between 0 and 1. If R-square is closer to 0, it means the regression model has very little explanatory power to explain the variation in y. If the R-square is closer to 1, it means the regression model can explain the variation in y pretty well. Ideally, the closer R-square is to 1, the higher is the explanatory power of the model at predicting y. Note, for one variable regression, R-square is the same as a correlation coefficient between x and y. For the California school example, if we can estimate SSR, TSS, and ESS, then we can use these three metrics to calculate the R-squares of the model. In this case, R-square is 0.05. This means only 5% of the variation in test scores can be explained by classroom size, or STR. In other words, 95% of the variation in test scores remain unexplained by the model. For the wage example, we compute the R-square to be 0.16. That means 16% of the variation in average hourly wage can be explained by the classroom size. Can be used to explained by the number of years of education. In other words, 84% of the variation in hourly wage is still left unexplained by the model. Now let's pause to take in-class exercise number 4. The second measure for goodness of fit for linear models is SER, or standard error of the regression. SER measures the standard deviation of the regression error U, or how spread out are the observations around the regression line. The variance of the regression residual can be estimated using SSR divided by n-2. The reason why the denominator is n-2 versus n-1 is because we need to use two efficients, beta naught and beta 1, in order to compute SSR. Hence, we need to adjust the degrees of freedom in the sample by using n-2 in the denominator. Once you calculated the variance of residuals, you can take a square root of the variance to get a standard deviation of the residual, and that gives you the SER measure. Theoretically, we want SER to be as small as possible. A smaller SER suggests that the observations are located closer toward the best fitting line. A bigger SER suggests that the observations are further away from the best fitting line. However, the unit of measurement for SER is dependent on the unit of measurement for the Y variable. And therefore, you have to compare SER against the scale of the Y variable to make sense of how tightly the observations are wrapped around the linear line. But this problem makes SER less intuitive to use compared to the R-square measure. For the California school example, SER is 18.58. It means that the standard deviation of the residual is 18.58 points. Since the test score is on a 100-point scale, the SER of 18.6 means that there is a large spread of the scatter plot around the regression line. This means that a prediction of the test score by SER alone will often be wrong by a large amount. As we can see from this graph, the observations of the test scores are very spread out around the linear fitting line, making this prediction model not very accurate to use. In the wage example, the SER is 3.38. It means the standard deviation of the regression residual is $3.38. Since the mean of which is $6, the SER of $3.38 means a large spread of the scatter plot around the regression line. In other words, the prediction made by this linear model is likely to be wrong by a large amount. Here you see how the scatter plot and the linear fit are like. Again, since the data points are very spread out from the linear line, the linear model is unlikely to deliver a very accurate prediction of the average hourly wage. Now let's pause to do the in-class exercise number 5. In summary, the OLS line is very sensitive and very intuitive and easy to use. In certain cases, it represents the underlying data well, and we can use it to make inferences about the population. However, there are also pitfalls for using the OLS line to capture the underlying data. For instance, the OLS line is very sensitive to outliers. Since it's a linear line, the linear fit doesn't represent the underlying data well if the data is not linear. Also, we need to always pay attention that the correlation doesn't imply causation. What we want ultimately is to use the linear models to establish causal relationships. We will examine this problem more extensively in the later part of the course. Here is a famous example that illustrates the problems faced by linear models. in the first plot, the data is linearly distributed, and hence the linear model appears to explain the data pretty well. In the second plot, the data is not linear, and therefore by fitting a linear model on the data doesn't really explain the underlying data. In the third plot, most of the observations, except for one, is linearly distributed. However, due to the existence of this one outlier, the estimated slope and the estimated intercept are biased. If we were to remove this outlier, the slope of the line will decrease and the intercept of the line will increase. In the fourth plot, again, the estimated slope of the linear line is very heavily influenced by this one outlier right here. If we were to remove this one outlier, the slope of the line cannot be estimated anymore because the line becomes a vertical line. And for a vertical line, the slope is infinite.